Hi, this is the third video on differential equations. So for the next 2 or 3 videos, we're going to be looking at differential equations in a context. So it says here, the end is here, so we're almost at the end of the A-level. It says maths couldn't be any more in context. So this is sort of everything coming together, all the skills that you've done with integration coming together in some contextual questions. It uses ideas from differentiation. It uses things that we did on connected rates of change. If you remember doing that, where we use the chain rule in a context, that comes into it. Proportionality. So there's a lot that it involves. In some questions, you will be given the differential equation, and it'll just be in some sort of context. Sometimes you might need to form the differential equation from the context, and that generally tends to be the tricky part. Although it says in that last sentence there, in reality, if you have to form the differential equation, it will be a show. It'll be a show question. That's often the hardest part of the whole question. But because it's a show question, it doesn't mean then that you can give up on it. It means that if you can't do the show part, then at least you can then go on to do the separation of the variables and the integration. So they tend to they'll either just give it you from the start and you'll just have to work with it, or you'll have to show it from the context. Either way, you should then still be able to separate the variables and do the integration. So before we sort of look at massive questions where everything is involved, it's probably worth just looking at just the forming part to begin with. Looking at the sort of language that you might have to do. Sometimes it involves proportionality, others not. Sometimes it involves connected rates of change, others not. So we'll just look at the forming in this particular video of the differential equation, and then we'll go on to look at some complicated questions then where we have to form and then solve. Okay, so let's look at a couple of questions. It says in the decay, so I'm just going to highlight what I would consider to be the key words here. In the decay of radioactive particles, the rate at which the particles decay is proportional to the number of particles remaining. Write down an equation for the rate of change of the number of particles. Okay, so first of all, we need to introduce a letter. Okay, so because we don't have anything to represent the number of particles, so I'm just going to call the number of particles n. So I'm just going to call it n. So let n equal the number of particles. I could have called it P for particle, makes no difference whatsoever. Okay, as long as I state what I'm calling it. So n is the number of particles. Okay, now this word rate, you've seen this before. If you see the word rate, it means differentiate. And when it's in a context, it's with respect to time. Okay, it says, in the decay of radioactive particles, the rate at which the particles decay is proportional to the number of particles remaining. So the rate of change of the number of particles, I can call dn by dt. So that is the rate of change of the number of particles. and it says that is proportional. So fish, or proportional, I've always called it fish. That's the proportionality statement, is proportional to the number of particles remaining. So that's proportional to n. Okay. The only thing that we are missing is the fact that it is decaying. If something is decaying, then it's decreasing, which means we need a negative. Okay, so that's called the proportionality statement. dn by dt, the rate at which the particles is decaying, is proportional to the number of particles remaining. To get that into an equation form, you can remember from your GCSE, then we just need to then put an equal sign and then introduce the constant of proportionality, which is usually a k. So I'm going to use a k. Doesn't have to be a k, but you will have probably used a k at GCSE. Okay, and that's it. And you can see there, then, we have got a differential equation, which if we then had to go on and solve that differential equation, we would have to separate the variables because the n is on the wrong side. Okay, so that's the first question. In the next question, a population is growing at a rate proportional to the size of the population at a given time. Write down an equation for the rate of growth of the population. So very similar to the last one. If I say P, I'll use P for population. Then the rate of change of the population, dP by dt, is proportional to the size of the population at the given time. Okay, so there it is, statement of proportionality, which we can then make into an equation by putting an equals and including the letter K. Okay, slightly different one. Newton's law of cooling, so this is Isaac Newton's law of cooling, states that the rate of a loss of temperature of a body is proportional to the excess temperature of the body over its surroundings. Write an equation that expresses this law. Okay, so let's think about what the variables we've got here. We've got a temperature of the body, so let's call that T. So T is the temperature of the body. And then we've got, well, the other thing we need to know is it's proportional to the excess temperature of the body over its surroundings, then we need to know what the temperature of the surrounding is, the surrounding temperature. So we'll call the S for the temperature of surroundings. So to give you a numerical example, let's say the temperature of the body is 20 degrees and outside is 25 degrees, then the excess temperature of the body, there'll be a difference of 5 degrees. Okay, so we need to know what the temperature of the body is and what the temperature of the surroundings is. Okay, right, it says the rate of loss of the temperature of the body, so d big T by d little t, is proportional to the excess temperature of the body over the surroundings. Well, how can we write that? Well, if it's the excess temperature, it's the difference, isn't it, between the temperature of the body and the temperature of the surroundings. So that's going to be T minus S. Okay? The only thing I've not mentioned is the fact it's the rate of loss. So that needs to be negative. Okay? So that's the statement. If we turn that now into an equation, we need to put a K there and an equals. Okay, so the first two are super easy. This one's slightly more complicated. Okay, so it's worth just practicing those. Okay, but they can get a bit more complicated, as you'll see in this one. The head of a snowman of radius r centimetres loses volume by evaporation at a rate proportional to its surface area. Assuming that the head is spherical, that the volume of a sphere is 4/3 pi r cubed and the surface area is 4 pi r squared, write down a differential equation for the rate of change of radius. Okay, so we've got the first sentence and the last part of the second sentence is to do with the rate of change. The middle bit is just giving us some formulae for the sphere. Okay, so I've not highlighted anything in the middle. It's the bits at the start and the end that are going to help us form our equations. Okay, so the head of a snowman of radius r centimetres loses volume by evaporation at a rate proportional to its surface area. Okay, so we've got A is, we'll let A be surface area. We'll say V is volume, R is radius. Okay. It's losing volume at a rate. So the rate of change of the volume, dV by dt, is proportional to the surface area. So it's proportional to the surface area, but it's also losing volume, which means it's negative. So you've got the rate of change of the volume. The rate that the volume is changing is proportional to the surface area, but it's losing volume, which means it's a negative. So we've got dV by dt is negative Ka. Whoops. So that's what we get from the first sentence. Okay, it says at the last part of the second sentence, write down a differential equation for the rate of change of the radius. So we're after dr by dt. Now hopefully this is making you think of something we did in differentiation. Okay, we've got something for dV by dt, but we're actually after something for dr by dt. So hopefully you're thinking connected rates of change here. Okay, dr by dt. If I use the chain rule, I can connect the volume with the radius. dr by dt will be dV by dt times by, and then, well, we're going to need the dV to be on the bottom, so it cancels out, and we're going to need a dr at the top. Okay, so that bit there is the bit that connects them together. So to use dr by dv, we need something for the volume in terms of the radius. Well, we've got that. It says the volume is 4/3 pi r cubed. So the volume, if the volume is 4/3 pi r cubed, then dv by dr, if I differentiate that, remember pi is just a constant, so we've got 12/3 pi, 12/3 is the same as 4, so 4 pi r squared. So I brought the power down and I've taken one off the power. Okay, right, so we'll put that in here. dr by dt is dv by dt, which is negative ka, times by dr by dv, so 1 over 4 pi r squared. Okay, so dr by dt is negative ka over 4 pi r squared. Now then, we're not quite there. So we're after a differential equation for the rate of change of the radius, which we've sort of got, apart from we've got too many variables. We've got an r, we've got a t, but we've also got an a. And we can't solve a differential equation if we've got 3 variables in it. Okay? So, can you think of a way that we can get rid of one of those variables? Well, it's to do with this. We are told the area is 4 pi r squared, so we know A is 4 pi r squared. So if I replace the A with 4 pi r squared, then all of that, change colour, all of that and all of that cancel out, and we're left with something really nice, which is dr by dt equals negative k, and that is our differential equation for the rate of change of the radius. Okay, so you can see there's 3 different levels in terms of difficulty. You've got your really basic ones, you've got one that's slightly more complicated when there's more variables, and then you've got ones where there is connected rates of change. So always write down the information that you've got, think about how you can write that in differentiation notation, and if it's not the one that you need, then you need to think of a way of using the chain rule to connect them together. Okay, so have a practice on those, and then the next video we'll look at forming and solving.